we'll have a talk from Patrick Legresley from Baidu. Patrick is a research scientist in the Baidu Silicon Valley AI lab, where he works on hardware and software systems for deep learning. Previously, he has worked at NVIDIA and Stanford University and has done research and consulting in parallel and high-performance computing for many application areas. He holds a PhD in aeronautics and astronautics from Stanford University. So today we'll be talking about HPC approach to training neural networks in deep learning. So let's welcome Patrick.
Thank you. So this morning, Dale Sutter talked a little bit about deep learning and some work done at Google, and then later some work using GPUs. This is kind of the next chapter in the story. So the Google Brain project was led by Andrew Ng, who is now the chief scientist at Baidu. And then Andrew Coates, who is one of the collaborators on GPU work, is the director of the Silicon Valley AI Lab. He's been responsible for starting that lab from scratch last June, starting with no people, no computers, no software, but a challenge to develop AI technologies that would impact at least up to 1 million users. And we heard also this morning that machine learning is all around us. So when Yelp assists us in finding a good restaurant, or we ask Siri the weather, or I use Baidu Translate to help you read emails sent to manufacturing from Beijing. That's all based on some sort of machine learning algorithm. Those are all available today, but in the not too distant future, we're going to have self-driving cars. My wife's really excited about that. She does my driving. I'm personally more excited about Pierre Beale's work at Berkeley on teaching a robot to fold laundry, because I don't like folding laundry. But these are fairly challenging problems. If we look at the typical machine learning approach to this, when we tackle some sort of problem like finding coffee mugs in photos, might go through a process like this. We'll collect a bunch of data, and then there's this step here, feature extraction. You see the magic one here. It's because this is where some difficult things happen. A human has to sit here and look at this and decide what sort of features are important in terms of identifying mugs. So what do you think looking at these pictures is important in terms of features you want to look for? So a loop handle, anything else? Some sort of cylinder or ellipse, like the opening of the top of the coffee mug. So excellent work. We identify features, and then we'll incorporate that into a classifier, and based on the features we find, decide yes, this is a mug, or no, this is not a mug. Maybe some with a probability attached to it. But what happens if we want to look for an automobile? Are these features going to work? No, I need to repeat that process. And I might look for features like tires, right? Now the problem is motorcycles have tires, cars have tires, so this all gets very complicated. So the idea around deep learning is I'm going to want to remove the human from the loop here, and I want the algorithm to learn those fundamental features. So I'm going to start with some data, and via an iterative process, I'm going to work through, and the algorithm should figure out potentially some low-level features like edges, curves, etc. And eventually we'll come up with some higher-level features. It won't really know that they are cylinders and handles, but if you human looked at it, they would know, hey, those are cylinders and handles that have been identified. And then ultimately, we could classify images, yes, there's a mug there, no, there's not. So instead of this human in the loop extracting features and hand-tuning it, we're going to use lots and lots of data and let the model determine these features. So if you like your data in picture form, here's another way to think about this. With the traditional hand-developed features, human is along here looking at the results, tuning in, and that tends to asymptote out at some point. You really can't get further improvements in accuracy, even if you have a lot more data. On the other hand, the problems of deep learning is you get more and more data, it will get better and better at doing this. if everything's working properly. So what exactly is deep learning in terms of algorithms? So it's typically biologically inspired about how the human brain works. And so I'm going to start with a relatively simple artificial neuron. And the neuron receives inputs either from the outside world or from other neurons. It applies weights to scale those inputs. It takes the sum of those scaled inputs, typically runs it through a long invariant to turn this into some sort of probability, and then it outputs this either as the end result or more typically as input for the neurons. Now, we're typically going to need a lot of neurons, and a typical way to think about the arrangement of the neurons in an artificial neural network is as various layers. So one side will have the input layer, so this is where the images would come in, for example. Each of these neurons then has outputs, potentially fully connected or some potentially sparsely connected arrangement to a next layer. This layer here is not connected to either the input or the output layer. I'm sorry, it's not the input or output layer, it's a layer in between, so it's a so-called hidden layer. And then I can build up potentially very complicated versions of this by having, of course, outside the scope of PowerPoint, lots of neurons and potentially lots of layers, potentially millions of neurons, billions of connections. And so some people, will say, well, this is like a super complicated thing, but if you really just think about this as it's a function that takes an input and generates an output, it happens to be a tremendously complicated function because of the large number of neurons and all these weights, but fundamentally, from a mathematical perspective, that's all that it really is. Okay, so I said the AI lab was started from scratch in June, and its challenge was to develop AI technologies to impact hundreds of millions of users. And the topic they chose to start with, so bringing the lab up, is speech. So why do they want to tackle speech? Well, if you're from the 24th century, you're going to expect your computers to be able to, be spoken to and do things and then come out to tell you what you're doing. And that's because speech is just a really universal interface. And you talk to your phone, talk to your watch, etc. It's a very natural way to communicate with various devices, especially as they've gotten smaller and it's no longer possible to have a keyboard on your watch, for example. So just to say a few words about traditional approaches for speech. Again, hands-on development of features by experts, sometimes from the neuroscience or the linguistics community. And typically they went through small incremental approaches. Someone had an idea and they got a little bit of an improvement and so on and so on. But it's a very labor-intensive, time-consuming approach, and it didn't yield tremendous benefits with large amounts of data. The other thing is, it may not generalize very well. So, for example, English and European languages are typically non-tonal. Pitch doesn't matter. So the features you develop for a non-tonal language may not work in a tonal language like Mandarin. So your efforts may not apply to all languages. So MFCC is one of those examples where they throw out pitch. It's not something that's applicable to Mandarin where pitch is important. Baidu being a Chinese company, being able to tackle Mandarin is a very important capability when we're developing speech recognition. So deep learning for speech, instead of sitting down and trying to figure out all these features, could be applied to tonal versus non-tonal languages, etc. We're going to get rid of all that. As input, we'll have a linear spectrogram. So we'll go through and take the sound signal, look at windows in time, compute the FFT, and get a power distribution over time. We'll run this through my little artificial neural network here. And then at the end of that, I'm going to have the speech transcription of what did the user just say. Now, speech is maybe a little bit trickier than looking at a static image because it has a time component, right? So if you ever been in a conversation with someone and you didn't quite understand the word, but then the follow-on words allowed you to figure out what they had said previously? So speech recognition benefits from being able to look at both directions in time. So the reality is that for speech, you're typically dealing with temporal data benefits from a little bit more complicated networks. So for example, we typically use a bidirectional recurrent neural network, which means not only are we going over the data in the forward direction, forward in time, we're also looking to the future a little bit and coming backwards in time. And this could be done for all of the layers or maybe just a few of the layers. You try to minimize this because if you want to do real-time speech, this introduces lag because you have to wait for data to figure out what was going on in the past. Okay, so if a neural network is a really complicated function, how are we going to develop it in some automatable way? Well, one typical approach is to use what's called supervised learning, and that means that I have labeled data. And in the case of speech, labeled data will be various little utterances that people have said, for which we know the actual correct output. So somewhere we have a wait file of someone saying call home and tell them I'll be late, and there's a corresponding reference, text file that says that's what that wait file represents, and so on and so on. And what I need to do is figure out the weights such that when I input this, I get this, and when I input this, I get this, and so on and so on. So it really just comes down to a very large-scale optimization problem. Start with some random initialization of the weights, and then start adjusting them so that as I run all this label training data through, I get a set of weights such that, in some sense, I minimize the error over all of this data for which I know the answer. And then hopefully, if I've done things well, that will generalize to data that I've not seen yet. So there's various different ways you can do optimization problems. Fortunately for these neural networks, we can use gradient-based optimization. And gradient-based optimization just means you have some sort of function, you have to get it placed, you get the derivative, and the derivative tells you the minimum is somewhere this way. I don't know how far away it is, but it's in that direction. So I'll move a little bit in that direction, and then I will update the computational gradient, and then it's going to tell me, yep, it's still this direction, so on and so on. And it doesn't matter where you start, whether it was here or here, you'll end up with this minimum. This is telling students it's a convex problem, and if you want to get the global minimum, you rather not have a lot of little bits and stuff, otherwise you may get stuck in a local minimum. The application to this in deep learning is it's not going to be a one-dimensional function. I'm going to be computing the gradient of the area with respect to like billion parameters, all these different weights. And the AI community calls this backpropagation. It's really just a chain rule. So what I do is I have all the labeled data. If I try to use it all at once, I would hit memory constraints pretty fast. So the data is typically split into what are called MVAPICHs, which just says give me the first 256 sets of labeled data. I'm going to run those through, do stochastic gradient descent, which means I get gradients that aren't quite right, but they're close enough to get them progress towards the minimum. And then I move to the next step, and so on and so on. Eventually, I work my way through all the data into what's called one epoch. And then typically, I repeat this multiple times to get closer and closer to the minimum until I'm satisfied that it's sufficiently minimized. I pick off the cluster because someone else wants to use it. Okay, so I'm solving this really big optimization problem. but they need lots of data. And so one of the big things that the lab had to do was gather all this training data, and I'm not going to go into the details of that. There are existing data sets like the Wall Street Journal set, I think has like 80 hours of labeled training data. The Baidu data has somewhere around 6,000 to 8,000 hours of English training data. You can also take training data and synthesize additional versions of it by artificially adding noise. So oftentimes when you're talking to your phone, it's in a noisy environment, right? So one of the things you want to be good at is understanding people even in the presence of noise. So you can add noise artificially. The computational requirements of this are pretty substantial. So it takes tens of exaflop of computations to train one model. We have a lot of advantages, though. We don't need double precision floating point. We can use 16 or 32-bit floating point. And because this process of propagating things through the network can be expressed as gem operations or convolution, depending on your network, GPUs are excellent for this because they have very high computational rates for these sorts of computations. And that's also helpful because creating a model is still a bit of an iterative process. Should I use 7 layers? Should I use 12 layers? How many bidirectional recurrent layers do I need? How many neurons do I want in each layer, et cetera, et cetera. So there's still an experiment aspect of this, but it's much more decoupled from the actual data. I'm not thinking about cylinders and handles so much anymore. So this is an approach that was published by Jeff Dean and others at Google in 2012 on training neural networks using a more loosely coupled approach. So they have what they call a parameter server up here. So this is the single point that maintains essentially the reference model. And they replicate this on all these other machines and they're computing updates. So W is the input weights. What the weights are right now, delta W is the update to the weights. And to get performance out of this, they go asynchronous. That's fine. To get additional performance, they go lossless asynchronous. So they have inherent rate conditions. And they get by with that because essentially you don't truly need perfect gradients. As long as they're close enough, it's sufficient to make progress in the optimization. However, what they're giving up is determinism. Every time they run their code, they will get slightly different results. And I didn't mention I'm actually educated as an aerospace engineer, PE software, movements and structures, that kind of stuff. Not getting deterministic results, and every time you write code is a little disconcerting. Probably is to a lot of you as well. It can also mask very weird bugs because uninitialized memory is kind of, stochastic as well, right? So we feel the results should be replicable and non-determinism is essentially a bug. If we find that for any given instance of time our code is not deterministic, there's an effort that goes on to figure out why it's not deterministic and we fix it. And we feel that both performance and determinism can be achieved if you adopt a more closely coupled HPC approach to training these neural networks. So this is the infrastructure in our AI lab. So on the software side, we use CUDA, of course, for our GPUs, use MPI, including MVAPICH, and then Majel is an internally developed library from the lab that I'll talk about momentarily. We use Tight-Next GPUs because we want to use the Maxwell architecture, much faster than the CUDA architecture for what we're trying to do. We pack 8 of these guys into each of our 4 U servers. Those guys have 3,200 watts of power supplies in them. And then everything's linked together using non-SFDR interconnect. So a very HPC-centric approach. So just a little bit about what Majel is. Any guesses on why it's called Majel? Majel Roddenberry was the wife of Gene Roddenberry, and she served as the voice of the computer in Star Trek. So it's a reference to speech in Star Trek. So that's what it's named for. But Majel is a C++ library for multi-dimensional contiguous in-memory arrays. So unfortunately, C++ doesn't have this out of the box like Fortran, so you have to kind of develop it yourself. It also has Python bindings, and the other, of course, interesting thing for us is CPU GPU aware. An array can be on the CPU or the GPU, can be copied back and forth. We manage a memory pool for dynamic memory, either in the CPU and or the GPU. If we run out of GPU memory, we can fall back and allocate things in CPU memory. And you can kind of think about it as like linear algebra, kind of like a NumPy type library where you have multivariate vector matrix operations, convolution. We use NVIDIA Cublocks and cuDNN. We also use libraries from a company called Neuron Systems. That's a company trying to do specialized hardware for AI, but in the meantime, they're also doing things with GPUs. They're a really, really smart guy that's handwritten in true assembly some of these kernels that exceed the performance of NVIDIA's libraries. And then we have reduction operations for a single GPU or distributed over CPU, GPU memory, which internally are implemented, as a combination of kernels, MPI calls, etc. So we have a few different approaches to parallelism. One of the approaches is we can do what's called model parallelism. So if this is my neural network, one of the things I can do is split it up, do kind of a domain decomposition. I put this particle model on one GPU, which is associated with one MPI ring. I put the other half of the model on another GPU, associated with another MPI ring, and then of course communication has to happen. There's also what's called data parallel, and I really hate this term that the AI community came up with because it has nothing to do with data parallel as we think about high performance or parallel computing. It's in the sense that if you have this labeled training data, you can send stuff to different instances of this and have them be computing updates to the weights, etc. And we keep those synchronized by doing MPI called reduces. So I can combine model parallelism and I can also do data parallel and split up my training data as well. So two directions there for the parallelism. The other possibility is more recently we've been doing kind of a more sophisticated approach with a distributed array where you have these big matrix of these gradients, whatever, and I split that up typically by rows in our case, and I assign big chunks of it to each MPI ring, which is each using one of the GPUs and one of the cluster nodes. The nice thing about this is it does reduce the per GPU memory requirement. So if you find 12 gigabytes constraint, you can split that up across multiple GPUs. It is more latency sensitive, whereas the data parallel or the model parallel is more bandwidth intensive. But again, you can actually combine this with model and data parallel. So we can have model parallelism, split the model across GPUs. We have multiple instances, each looking at different pieces of training data, and within those we can use the distributed array as well. And we think this will probably be more important for future scalability. So to talk a little bit about performance. So if I start with baseline performance on 4 GPUs using an MVAPICH size of 256. In other words, 256 speech utterances being processed simultaneously to do the gradient descent. That's my baseline performance. If I want to do strong scaling, I keep that MVAPICH size the same and I increase the number of GPUs. And that's what this line is. So what's happening here is obviously efficiency is going down significantly. The problem is, as we apply more GPUs to 256 utterances, the gem operations are going in a direction where they are more bandwidth limited than compute limited. So they're approaching a MVAPICH instead of a gem. And that's why we're losing performance here, because of the balance of bandwidth versus compute on the GPUs. However, we have a different thing that we can do, which is, as we increase the number of GPUs, we can increase the min-batch size and present to each of the GPUs more data. So it's a form of weak scaling. So if we come along in this direction, we're increasing the min-batch size, and you can see that for what we're typically doing right now, which is training one of these models on 8 to 16 GPUs, we can sustain about 85 to 95% of 4 GPU performance. Well, why don't we use more GPUs? Well, one of the goals of the systems team or network is efficiently using our hardware. And our metric for efficiency is we want to sustain at least 50% of the hardware peak, which in our case is limited by FMA on the GPU. And we can sustain around 60 to 65% of the peak using a single GPU. Out to 8 GPUs, we are right around 50% of the peak. And again, if we want to utilize the rest of the cluster, well, we have lots of researchers that want to try different model ideas, stats, comparison, and parallel. And so to maximize the overall throughput of our cluster, this is basically what we restrict our users to at this time. As we make improvements and can maintain that throughput with more GPUs, we can do that and decrease the latency of training an individual model. But as of that, the model training time for our speech work is on the order of a few days, depending on the complexity of the model. And as I said, the lab was started from scratch last June. Being that most of the people in the lab don't speak Mandarin, the initial work was done in English. But at some point, Baidu wants to see Mandarin. So in February of this year, we did our very first work with Mandarin. And what's being plotted here is character error rate. In other words, the percentage of the characters that are mispredicted over time. So you can see that in about 4 months, we got down to a character error rate of 6%, which is on par with the best systems in the world. Despite the fact that we don't speak Chinese, and we initially wrote the system for English. The only real change we had to make was to deal with performance issues on the fact that English has around 30 characters, and there were apostrophes and things. Chinese has thousands and thousands of characters, so somebody raised that figure and just needed to tweak a few things, but it did not affect results, only performance. So what are some of the challenges and opportunities that would be interesting for you to take away from this? The first one that I wanted to mention is the memory allocation takeover when we use InfiniBand. We're very aware of the reasons that this has to be done, because the page table translation can't be done by the channel adapter. It caused us a lot of problems because each of our speech utterances is of different lengths. And so that's basically why Majel has support for being a heap manager. We allocate all our memory up front at the beginning of training. That takes a little bit of time because it has to be page-locked. But then we manage the memory out of that. So we actually prefer, maybe more than CUDA model, where we can be a little more selective on which memory is subject to this and which isn't, because the vast majority of the memory we're working with is never going to be communicated anyway, but it's kind of this all or nothing approach. I do know that in the future, Malnox will support page table translation in the hardware, so maybe that just goes away. The next thing I wanted to mention was machine topology. So this is a top-down view of one of our type nodes. Supports 8 GPUs. So these are the CPU sockets right there. These little silver rectangles are PLX PCI Express switches. And these are by 16 slots for each of the 8 GPUs. This is a fairly complicated topology. Pairs of GPUs can communicate very quickly. The 4 GPUs are still part of the same peer group, so they can do peer-to-peer. But the 4 GPUs on this side have to communicate by going through PPI back to the other side. We had to do a lot of work to get to the point where we were getting 50+% of peak. I would say that MVAPICH is probably provided the most set of tools around this compared to some of the other implementations, but we still found it to be pretty challenging, despite the fact that we have some really talented people in our systems group. So things you can do to make life easier in that area would be useful. The other one is that when we were thinking about the programming model for how to do computations within one node, normally you think about that as shared memory, right? But then you look at the 8 GPUs in that shared memory machine, but that's distributed memory. So the question is, do I do one MPI process for the entire node? Do I do one MPI process for each socket, each controlling 4 GPUs? Or, since I have 8 distributed memory spaces, do I do 8 MPI processes, each controlling 1 GPU? It's kind of a natural fit, right? And it makes you, or it helps you in the sense that you're kind of oblivious in some senses to whether the GPUs are even in the same node or not, right? But remember, we're really concerned about hardware efficiency, and so one of the things we look at is the efficiency of that approach versus, just one MPI process using, for example, peer-to-peer under CUDA toolkit. So we always do comparisons of how fast can we get data back and forth using peer-to-peer versus how fast can we do it with MPI sends and receives. And personally, our benchmark is if we get 80%, that's really all we expect. Anything above and beyond that is just great. But in some cases, particularly when we have to cross QPI, we do not see that. So the other thing is we've had lots of issues with problems with the PCI Express topology, problems with the driver, the NVIDIA driver, and sometimes CUDA where MPI just doesn't work at all. And it's required significant interaction with our hardware vendor, the motherboard vendor, NVIDIA, etc. So I know that's not your fault, but you might want to be aware of this. And when you see opportunities to address something like this, you might be able to help not only us, but others in the community out in that regard. So, pretty much out of time, but just to wrap things up, neural networks sound pretty complicated, but I think in reality they're fairly simple, especially if you come from kind of a traditional high-performance compute background where you're used to a lot more complicated things, PEs and stuff. As I said, with the systems team, so we work towards achieving deterministic results, application performance greater than or equal to 50% hardware peak, and ultimately we want to get strong scaling for multiple GPUs across multiple nodes. We are working on addressing that, and I really just want to emphasize that AI via HPC is something that will impact hundreds of millions of people, because the ability to talk to your phone, get in your car, how to drive, use somewhere, etc., is really life-changing. And just a plug for recruiting, we are always looking for more systems researchers with backgrounds in parallel computing, architecture, storage, etc. And if you want to find out a little bit more about this, this is a quick little tutorial. This is the publication from the AI Lab, and this is a recent blog post about the work in anchoring. So if there are questions, well, that's setting up. I also have a quick little demo here we can try out. So this is just a little web interface that allows us to do some little demonstrations with our speech recognition. Since I'm assuming English is the lowest common denominator here, my internet sucks, so stick with English. So we're talking about using GPUs in InfiniBand for deep learning. So far the main focus of the lab has been on developing a model. We're starting to do research on production and increasing or decreasing really the time from getting the data to returning the transcription. So in this case, I got a perfect transcription. Despite my best efforts to get it to return MVAPICH, I cannot get that to work. So if you'd like to provide us with some label training data, we can fold that in and improve our performance on that takeover. So thank you. Any questions? Yes.
You mentioned your boost when you try to use GPU Direct or CUDA Aware MPI. I was wondering.
So GPU Direct doesn't work with GeForce cards.
Yeah, exactly, that was my question.
Right.
So because you're using the Titan X and that
Yeah,
doesn't
so it's
really...
a conscious choice that we prefer the Maxwell architecture over GPU Direct.
Okay, so I mean, there are other Maxwell boards out there which probably on the Quadroline, not sure if they support that.
NVIDIA has not productized the Maxwell architecture in the Tesla product line.
Right. So the K80 wasn't an option either, I guess.
It just comes down to performance. The Maxwell architecture is so much faster for what we want to do that we prefer that.
I see.
The one with the microphone, yes.
I'm just. Can you say like how many weights at the end of the day do you compute to sort of drive that back in?
Somewhere in the millions to billions, depending. Now that we're starting to get towards production, we're trying to reduce the amount because the production cost of processing each utterance is in some sense going to be proportional to the size of the model. So we were happy with our progress on the actual accuracy of the model, and now we're trying to maintain that same accuracy and get a model that's better for actual deployment into production.
I just wanted to ask, how is MPI working for you as a programming model? Do you think that MPI, as it's defined, is working well, or do you need changes to it?
I think the model is working pretty well for us. One of the things, so I come from a more traditional high-performance computing background. I've used MPI for 15 plus years. It's very comfortable to me. One of the things we run into is I think we use it in a little bit different ways. For example, our all reduce will reduce millions of values. So OSU benchmark does a latency benchmark, right? We want the all reduce bandwidth benchmark to be optimized. Although certainly long term, as I said, all reduce is fairly expensive, and we are moving more towards the distributed array approach. But depending on the state of different organizations and their ability to do parallelization, this may be of interest to the deep learning community.
So what do you mean by distributed array approach?
So the distributed array where I take the big matrix and I take the first big chunk of rows and I put them on.
Oh, this one.
So all reduce is really important right here because I may be all reducing the entire model depending on how many times I've replicated it for the data kernel. There's also a pretty significant amount that has to go on with the model kernel depending on how many connections are being cut when I do the decomposition. So this is bandwidth sensitive, all reduce. This is more latency sensitive in the sense that I'm typically only communicating around borders and stuff, so cable kind of stuff.
And at the beginning, you said that methods that worked on a non-tonal language didn't necessarily work with a tonal language. And in the middle, you showed how you just switched from English to Mandarin with...
Our system doesn't depend on whether it's tonal or non-tonal. It just figures it out.
So is that generally the case, or what is special about your system that doesn't matter?
So ours is more this deep learning approach where we take a huge amount of data, thousands to tens of thousands of hours of data, and let it figure out the low-level features, just like in the coffee mode, where it figured out lines and stuff, right? So it's figuring out a lot of these things for us. And it's hard in image processing, if you look at the first layer, that's typically where the fundamental features are, you'll see edges and stuff. It's hard to get intuition about the sound features because it's just a spectrogram and stuff. But it is discovering at those lowest levels the features that are important for a given language.
Thank you.
Any other questions? Yes. Adam.
Is Majel open source, or do you have any idea?
There's no current plans to open source it right now.
Are you aware of any open source MPI neural network frameworks?
So there are things like Cafe and Torch and some other things that can utilize GPUs. I'd be willing to bet that they can't sustain on the application level 50% peak across 16 GPUs. So we've done a lot of engineering effort to do that, but you can't utilize GPUs for some of the open source deep learning things.
Okay, yeah. I'm familiar a little bit with Cafe, but I don't know if they've added MPI at all.
So I think Cafe is limited to a shared memory. So I think NVIDIA has like the digits box, right? Where you can train on like 2 or 4 GPUs within one system. I don't think it has MPI support. I believe that's correct.
This one from Akshay.
I may have missed this point, but in one of the slides you mentioned that there's a 10 exaflop requirement. Is that a requirement that allows you to transcribe in real time, or I'm curious to know how you arrived at that?
You're talking about the going in both directions?
No, in one of the slides you said.
Do you remember which number? Which direction?
Yeah, I think that was. Go forward a couple of slides. One more. Yeah, so here you said tens of exaflop of computation.
Yes.
So how was that requirement arrived at?
How does that requirement arise?
I mean, what is an exaflop required for? I'm curious.
So each time we present training data, we have to propagate it through the network forward, compute the error, and then propagate it backward to get the gradients of the error with respect to the weights. And then we use those gradients to update the weights. And we're doing that for, in many cases, tens of thousands of hours of audio. So think about a full-time job for 5 years just to see the audio. We're going to run that through our system in a few days. So it just depends on the size of the network and the amount of data you use, but it ends up being tens of exaflop.
Okay, any other questions? So I think just to give feedback, so we'll try to see an all reduced bandwidth benchmark we can introduce, and we'll be happy.
And if you want to play around with the demo, I have it on my iPad and computer, so we can play around with it and see what it can and can't do.
One more quick question. Do you also use MPI in the classification task, or is it just in the training?
So in our approach to classification is largely built into the model, although you can also incorporate what's called a language model into this. What the model actually outputs is probabilities of each of the characters for a window of time, and then you have to do a search through that to find the most likely scenario. You may augment that with a language model that says, I know you think it's this, but based on our web crawl of hundreds of terabytes of data, we think it's actually more likely to be this other phrase. So that's why something like MVAPICH is difficult, because the number of occurrences of MVAPICH that appear in the text is pretty small. So you also need a better web presence for us to get that language model.
Okay, we'll provide you more training data, we'll publish more, so that it goes into your dictionary, okay?
You've probably done enough with the MVI implementation.
Okay, so let's give thanks again. So I think on the same topic, so now we have a follow-up thing from Abhinav. He gave the talk in the morning, so we can skip the introduction, but the topic is